rest 55 should also have benefit of the recording. So therefore I am recording. All right. Uh, yeah, two questions you have asked. Let me answer them one by one. Answer would be little long, but that's okay. Let's consider only two evaporators. Okay, so just so that it is easier for me to draw and it is easier for you to see. Uh, so here we are having 3% by weight NaCl solution, salt solution, seawater. This is our steam. This is our condensate. This water vapor is going as a heating medium in the jacket of the second evaporator. I will get condensate from here as well. Let me take another color just so that we can distinguish between different streams. So this is our 3 weight percent sodium chloride. So 3 weight percent sodium chloride liquid is inside the evaporator. This concentrated salt solution is going to the second evaporator. The product is coming from this evaporator. This we wanted, let's say 50% by weight NaCl. This first one, excuse me, first one is operating at atmospheric pressure. Second one is operating at less than 1 atmosphere absolute pressure. Now, so there are two ways in which we operate plants. One, continuous process. It operates at steady state. What does steady state mean? Steady state means any variable, when I say variable, what I mean as any process parameter does not change with time. Now, so if we are operating these multiple effect evaporators in a continuous process operating at steady state, meaning there are two evaporators. This 3 weight percent sodium chloride is coming in all the time. Steam is supplied all the time. Condensate is going out all the time. This partly concentrated solution is going from evaporator 1 to evaporator 2 all the time. The water vapor is getting vaporized all the time. It is coming to the second effect in the jacket all the time. Condensate is going out all the time. This 50% weight percent NaCl is coming out all the time. So if I look at any variable, when I say variable, I mean process parameter. Any process parameter, if you plot with respect to time, let's say concentration of this stream, concentration coming out of the evaporator 1, this is constant with respect to time. It does not change. Okay, so that's why we need to keep on we need to keep on maintaining this pressure at less than 1 atmosphere. We need to keep on maintaining this at 1 atmosphere. We need to supply steam all the time. We need to take out condensate all the time. This solution is going to get transferred from 1 to 2 all the time. So does that answer your part of the question?
I understood that. Okay, but then the second question still remains.
Yeah, second question I'm answering. At least the part of the question. Yes or no?
Yes, sir.
Okay. So the second question is the second, no, not the second question. The two ways in which we operate plant. So in the first case, when we are operating the plant continuously, so that's why we are giving this in terms of kg per hour, 100 kg per hour, right? Because it is coming in all the time. The flow rate is mass flow rate. Mass flow rate is 100 kg per hour, right? So it is 100 kgs per hour. It is the flow rate of that stream coming into the first evaporator. So for example, if you open your tap, water is coming out of the tap at the rate of, let's say, 1 kilogram per hour or 1 kilogram per minute, right? Depending on how much you have opened the tap. That's what we mean by a continuous process. That's why we are saying that it is the volumetric flow rate or a mass flow rate of the stream we specify, 100 kgs per hour, meaning that the volumetric flow rate, the mass flow rate of that whole stream coming in, it is flowing at a rate of 100 kg per hour. So if I take a 1 hour slot, if I take a sample for 1 hour, that sample will weigh 100 kgs. Okay? So that's why we are writing all the flow rates in terms of per unit time. Even the steam flow rate we wrote in terms of so many kg per hour. This product 50% by weight NaCl we wrote as 6 kg per hour. This water that evaporates from here, water evaporating from here, water evaporating from here, total water evaporation rate is 94 kg per hour. Right? So whenever we have continuous processes, it is not that we have charged something and stopped. All the time, every hour 94 kgs are coming in, and it is not just every hour that we at the start of the hour we put 94 kgs, then don't do anything for the next 55 minutes, and then another 5 minutes we add 94 kgs, then don't do anything for 55 minutes. It is not that. It is that the flow rate of that stream is mass flow rate of that stream is 94 kgs per hour. Do you understand that? Is that okay?
Yes, sir.
Second way of operating equipment is batch wise or a batch process. Now, whenever you have a batch process, right, what we will do is we will, so in here, process parameters change with time. Okay. Now, so if it's a batch process, what we will do is, suppose this is your first evaporator. Suppose we will put, let's say, suppose this evaporator capacity. So when I say evaporator capacity, what we mean is the amount of liquid that it can hold inside it. Okay? Suppose the evaporator capacity is 5,000 kilograms. That means what we will do is, one, we will fill 5,000 kgs of seawater in the evaporator at 30 degrees centigrade. Okay. 2, we will start steam to jacket. Right? So we will supply steam. Now steam will have to be continuously coming in, and condensate will have to be continuously going out. Okay. So what will happen? As I supply steam, heat will be transferred from outside to inside. Temperature of 5,000 kgs of seawater will start increasing. Will anything boil? Will anything evaporate? Arya, do you think anything will evaporate? At time t equal to 0, temperature was 30 degrees
No,
centigrade.
sir.
Yeah, temperature was 30
No.
degrees centigrade. Nothing will evaporate.
at t equal to 0, nothing would evaporate because
Correct. At nothing,
we haven't started
correct,
heating.
correct. And so as we start heating, nothing will evaporate till boiling point is reached. Do you agree
Yes,
with
sir.
that? Right. So it will keep on increasing. So it is picking up sensible heat. Now it will reach its boiling point. So this is suppose the boiling point of 3 weight% solution. Maybe the boiling point is 105 degrees centigrade. I don't know, based on ebullioscopic constant we can work out this. The temperature is not important. Now the solution will start now the water will start evaporating. So it reaches its boiling point. Now water will start evaporating. Now as water evaporates, what will happen? The concentration of salt in the solution will increase, isn't it? After some, it was initially, let's say 3%, here it is 3%. Now if we keep on hitting, slowly it will become 3.5%, 4%, 4.5%, 5%, 6%, 7%, 8%, 9%. It will keep on increasing. And as the salt solution temperature keeps on increasing, as the salt solution concentration keeps on increasing of the salt in the solution, the temperature will also start increasing. The boiling point will start increasing. So the temperature will increase slowly because the salt is getting concentrated slowly. So if I plot different parameters, so this is the temperature. If you plot salt concentration, so let's say salt concentration, this is 3 weight%. Slowly the salt concentration will keep on increasing. Right, I'm plotting different things on the same graph just to show you how things are happening. Right, so in the blue I'm plotting the temperature, in the red I'm plotting the concentration of sugar of salt solution inside that evaporator. Now as the water evaporates, what will happen to the amount of solution in the evaporator? Initially it was 5000 kgs. As water now starts evaporating, what will happen to the amount of solution inside the evaporator?
It decreases.
Correct, it will decrease. So if you plot in black the amount of solution, so till it reaches its boiling point, it was 5000 kgs. Now as the material evaporates, as the water evaporates, the total mass of the solution will start going down. And because the water is getting evaporated, the salt will keep on, concentration of the salt will keep on increasing. Because of the boiling point elevation, temperature will keep on increasing. If you plot the rate of evaporation, the rate of evaporation will also change, because now as the liquid level drops, suppose after some time it becomes here, 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 right? The amount of area through which heat is getting transferred, initially it was all this area that was heating was happening through all this area, heat was being transferred through all this area. After some time, the area through which heat is being transferred from outside to inside is only this much. Do you agree with that?
Yes, sir.
And
Yes,
if the area reduces, then the rate of heat transfer reduces, the rate of water evaporation will also reduce. So if you plot now water evaporation rate, initially it was 0, right? It was not boiling, it was just picking up the sensible heat. Then it will increase because now the boiling point has reached, and then as the level keeps on dropping from here to here to here to here, the water evaporation rate will also keep on reducing. So if I have to do a multiple effect evaporator for a batch process, I will have to store this evaporated water somewhere, right? There's no way I can store it. So there is no way I can do multiple effect evaporation in a batch process. Do you agree with that? So if I have to do multiple
Yes,
effect
sir.
evaporation, it will have to be in a steady state
Continuous
manner,
process.
continuous process, in a steady state manner. I have still not answered your question. Second question. Third way of operating is something called as semi-batch or semi-continuous, if you like. Okay. But the word semi-batch is more often used than semi-continuous. So what we will do is initially we will take 5000 kgs at 30 degrees centigrade. We will start the steam. Condensate will start coming out. Right? Temperature will rise to, let's say, 105 degrees centigrade. Water will start evaporating. And if water starts evaporating, now this liquid level will start going down. Right? So maybe after some time, maybe the liquid level has gone down up to here. Now we will start adding 3 weight% solution at 30 degrees centigrade. Okay, and then we'll start drawing out the product. Okay, so it is partly batch, it is partly continuous. That's why it is called as a semi-batch operation. We will see in your third year when you start doing biochemical reactions, fermentation for making, let's say, pharmaceutical products or drugs. Many times we use this a semi-batch kind of operation. There are certain advantages of using a semi-batch process over a continuous process. Okay, now to your second question. If your evaporator 1 this is operating at 1 atmosphere, let's say the second one is operating at, let's say, 0.8 atmosphere. Just take some numbers. This solution going into the second evaporator, this solution, if you see, let's say this temperature is 105 degrees centigrade. This solution going from evaporator 1 to evaporator 2, maybe it is like 8% by weight NaCl. It has a temperature of 105 degrees centigrade. It has a pressure of 1 atmosphere absolute. Do you agree with that?
Yes, sir.
Now, when it goes into the second evaporator, the pressure is only 0.8 atmosphere. Pressure is only 0.8 atmosphere. So if you think about the second evaporator, second effect, 0.8 atmosphere, the boiling point would be much less. Would be less than 105 degrees centigrade. So for this purpose, for the purpose of the second evaporator, it is as if this solution, which is at a temperature of 105, but now it has suddenly reached a pressure of 0.8 atmosphere. The solution now is superheated, and therefore that superheated solution, being thermodynamically unstable, will vaporize. Part of it will vaporize. Temperature will come down to the evaporator temperature. Maybe it will come down to, let's say, 95 degrees centigrade. So now the solution instantaneously will go from 105 degrees centigrade 1 atmosphere to 95 degrees centigrade 0.8 atmosphere, and the amount of enthalpy, the amount of superheat that this solution was carrying, will partly go in the evaporator vaporization and partly go out in the concentrated solution. Okay. The amount of water, so this process of sudden reduction in pressure making part of the solution evaporate, there is a nice name given to that process. It is called as flashing. Flash, as if you are taking a photograph and a flash, you press the photograph button, the camera flashes, right? So it is like that. It is a instantaneous kind of evaporation, as if there is a flash of vapor that is generated. That's why the name name that is given is flashing. So the amount of water that evaporates due to flashing will depend on 1 degree of superheat. Of the solution. What I mean by degree of superheat is what is the temperature and pressure. If suppose instead of 105, suppose the temperature was 145 and pressure was 3 atmosphere, right? It has much more degree of superheat when you are flashing it down to 0.8 atmosphere. So second, it depends on is the change of pressure. From 3 to 0.8, the amount of flashing would be much more. If it was 5 and correspondingly temperature was, let's say, 150 degrees centigrade, the amount of flashing will be much more. So the degree of superheat in the sense of temperature and change of pressure is from what initial or what pressure in evaporator 1 it is going to pressure in evaporator number 2. Okay? And this can be calculated. The amount of vaporization can be calculated. Okay? It will depend. Suppose this is an adiabatic evaporator. Suppose this evaporator outside the steam jacket, or maybe we take another kind of a situation that suppose just take water only. Suppose you take pure water, don't take salt solution right now. So assume that we have pure water. I mean, we can even do this problem just now. Suppose we have a pure water which is at 10 atmosphere absolute, 10 atmosphere absolute pressure. Let's say temperature is some temperature, let's say 180 degrees centigrade. It is a saturated, I should not say temperature, it is saturated steam. I flash it to 1 atmosphere. So suddenly we make the pressure 1 atmosphere in this vessel. We make the pressure we maintain the pressure 1 atmosphere. Part of the water will evaporate and partly it will be liquid water. If it is pure water, okay, obviously this remaining liquid water will be at 100 degrees centigrade and this water vapor will be 100 degrees centigrade. Do you agree with that? It is
Sir,
boiled
could you
off.
please repeat the...
Okay. Imagine we will do this problem. We will actually calculate so that you will know how to calculate. Obviously, the calculations will be more complicated if it's a salt and water system because you have to worry about enthalpies and concentrations and boiling point elevations and so on. But right now, imagine this is your evaporator. And we are maintaining this evaporator at 1 atmosphere absolute pressure, steady state. Okay. In this evaporator, steady state, we are supplying saturated water. Saturated water means suppose pressure is 10 atmosphere. Suppose pressure is 10 atmosphere absolute and corresponding temperature. Where will we get this temperature from?
Steam tables.
Correct, steam table. Okay, so we will actually get the, I will show you the steam table and we will actually calculate this value. Okay, now suppose now there is sudden change of pressure from 10 atmosphere to 1 atmosphere. So part of the liquid water will vaporize, partly it will become water vapor, and partly it will become liquid water. But because water vapor has formed, this solution must be at its boiling point. Gibbs phase rule. At same pressure, I have both water and in the liquid state and the vapor state. Do you recall our phase diagram for water? You remember this? If it is 1 atmospheric
Yes,
pressure, if pressure is 1 atmosphere, there can be only one temperature where both liquid water in the vapor state exists and water in the liquid state exists. And that temperature will have to be 100 degrees centigrade. Do you agree with that? For 1 atmosphere. Yes, no?
Yes, sir.
So this water
sir.
vapor will leave at 100 degrees centigrade. This liquid water also will leave at 100 degrees centigrade. Do you agree with this?
Yes, sir.
Okay. Now, do you people have steam tables with you, or should I share the steam tables on screen?
So sharing it would be
So
better.
please share it.
Okay. Yeah, but then you should download for yourself from Google, because now I have to write the values also, right? On the problem. So the problem is now the question that you were asking: how much water will vaporize? Right? So suppose I take 1 kg per hour of this saturated water. How many kg per hour of water vapor we will have, and how many kg per hour of liquid water we will have? Is that what you are asking, Arya?
Yes, sir.
So you don't have to take my word for it. We can calculate ourselves, right? So let's do this problem. Okay, I will share the steam table and then we will write all the values. Okay, let me open the steam table. So everybody please download steam table. Use your Google skills. Please download in the SI units. 1 second. Download in SI units so that we don't have to worry about things like BTU and so on. Open steam table. One second, it is opening. Why does it take so long? Ah. It's open. Okay, let me share now. Oops. Okay, are you able to see?
Yes, sir.
Yeah. So what was our feed? Feed was 10 atmosphere. So this is saturation temperature table in SI units. All right. Now it is temperature table, right? Table C1. There is also a pressure table. If you go down, saturation pressure table, right? So this is in terms of kilopascal. So 1 kilopascal. So you see this HF, enthalpy of the liquid. HF is enthalpy of the liquid. Hg is enthalpy of the vapor. HFG is enthalpy change for converting liquid to vapor, latent heat. Okay, pressure we want is 10 atmosphere. So 10 atmosphere. This is 100 kilopascal. That means it is 1 atmosphere, right? 1 bar. Suppose, let's not say 10 atmosphere. Don't worry about the atmosphere and bar. Let's say it is 10 bar. Okay, so 10 bar means 1000 kilopascal. Do you agree with this?
Yes, sir.
Okay, so 1000 kilopascal means 10 bar. Enthalpy of the liquid. How much is the enthalpy of the liquid? 762.23. Yes, no? Do you agree?
Yes, sir.
Okay, somebody note down this value. 762.23 is the enthalpy, specific enthalpy of the saturated liquid at 10 bar absolute pressure. What is the temperature? 179.87. Somebody note that down as well. Okay. Now, I'm going to get liquid water and water vapor at 1 atmosphere, 1 atmosphere, so 1 bar, let's say. So 1 bar means 100 kPa. 100 kPa. Temperature would be 99.63 degrees centigrade. Enthalpy of liquid would be 417.31. Are you able to see?
Yes, sir.
Somebody note that down. And enthalpy of the vapor steam would be 2675.27 kgs, kilojoule per kg. Somebody note down that value. Can we go to the problem now? You have noted down the values?
Yes, sir.
Let's go back to our problem. Okay, so let's say we are not talking about atmosphere absolute. Let's say we are talking about bar. Okay, bar, and they are approximately the same, 1 bar. Okay, what was the temperature of this saturated water? 179 point something degrees centigrade. What was the enthalpy?
762.3.
762.3 kilojoule per kg. Okay, specific enthalpy. Specific meaning per kg. Okay, what was the enthalpy of this liquid water? Specific enthalpy?
2675.27.
Liquid water,
So 417.31, sir.
417.31 kilojoule per kg. Liquid water, do you agree?
Yes, sir.
Yes, sir.
Water vapor, what was the enthalpy?
2675.27.
2.27.
27 kilojoules per kg. So now, if I say x kg per hour evaporate, this will be x kg per hour. This will be 1 minus x kg per hour. And if I nicely insulate this tank, if I nicely insulate this evaporator, put a thick insulation, nice glass wool insulation, if this evaporator behaves like an adiabatic evaporator, so what we are doing is adiabatic flash. Right? Do you agree?
Yes, sir.
We write that now. What kind of enthalpy balance can we write? 1 kg per hour, enthalpy coming in 1 kg per hour into 762.3 kilojoules per kg. Let me write it properly. Kilojoules per kg. Enthalpy coming in must be equal to enthalpy going out 1 minus x multiplied by 417.31 kg per hour, kilojoules per kg, plus enthalpy going out from the liquid, from the vaporized water, x kg per hour multiplied by 2675.27 kilojoules per kg. Right? Adiabatic. Whatever enthalpy comes in must be equal to whatever enthalpy going out, because no enthalpy is added, no enthalpy is lost to the surroundings. So can you find x? Somebody find x. Don't expect me to do it. Hey, what takes so long? Hello? Is the connection gone?
Sir, 0.1527.
Yes, sir. 0.1527.
Okay.
Yes, sir. 0.1527.
Okay. So only 15% of the water will vaporize. 15% of the incoming water. That too, the pressure change is from 10 bar to 1 bar. Okay. In your evaporator, the change of pressure is much less. The change of pressure is much less. It is from 1 atmosphere to maybe 0.8 atmosphere or 0.9 atmosphere. Do you agree? So only a small amount will vaporize. It will be not enough to vaporize this much amount of water vapor. That's why we will need this extra water vapor to be supplied as a heating medium. Now, does that answer your question, Arya?
Yes, sir. It does. It does.
So, point that I'm trying to make, I mean, answer to your question, Arya, the real answer to your question is yes, your question is valid. Right? Find out answer to yourself. Isn't it? How you can find out the answer yourself? Material balance, energy balance. I'm giving more of a philosophical answer that I did this procedure for you, I solved it for you, but you yourself can find answers to your own questions. That's what I'm trying to tell you based on material balance and energy balance. So yes, your question is correct, good, but you yourself can find the answer based on enthalpy balance. How much water would have evaporated if it flashed from 1 atmosphere to, let's say, 0.8 atmosphere? Would it be enough to evaporate the 33 kgs per hour of water that we wanted to evaporate? And answer is obviously no. All right.
Yes, sir. Yes, sir.
So, key to successful career: ask questions, find answers on your own based on material balance and energy balance. All right, can we go forward now? Slightly longish answer. I had warned you initially only. The answer is going to be long. Can we go forward?
Yes, sir.
Correct. We are,
Yes,
we, are, we are talking about enthalpy balances with reactions. We are talking about heats of reactions. Some of the things that we have seen are heats of reaction, standard heats of formation, standard heats of combustion. I hope you have revised all that. How to find heat of reaction from standard heats of formation, how to find heat of reaction from standard heats of combustion. Right? And standard means 25 degrees centigrade, 1 atmosphere, absolute pressure, standard conditions. And reactions will have products in their own natural state. So if we are talking about a reaction like this, the standard condition means H2O will be in the liquid. Okay, now let's go forward. We talked about how to estimate heat of reaction at different temperatures. Kirchhoff's laws that you have mugged up in your 11th standard, 12th standard, without knowing why we are mugging it up, without knowing where that law comes from. There is no such thing as that law. It is not a gospel truth. We can derive that Kirchhoff's law ourselves. Heat of reaction at any other temperature would be heat of reaction at 25 degrees centigrade, and integral of moles of the product, Cp of the product, moles of the reactant, Cp of the reactant multiplied by dt, integrated. And be careful about units of temperature. Sometimes temperature is given in terms of Kelvin, sometimes temperature is given in terms of degrees centigrade. Be careful about the units of Cp, units of delta H. The Cp can be in calories, delta H can be in kilojoules. So be careful about the units. The temperature limits of integration, that will depend on what are the units of temperature in the Cp equation. Cp, if I am writing, if temperature in the Cp equation is written in terms of degrees centigrade, these limits of integration will be in terms of degrees centigrade. If it is written in terms of Kelvin, it will be in terms of Kelvin. You will have to convert one from the other. Okay, so again to emphasize, the standard heat of combustion, meaning that H2O is in the liquid state. Standard 25 degrees centigrade, water exists as liquid water at 1 atmosphere. 25 degrees centigrade, 1 atmosphere. So water exists as liquid water. Okay? And if I want the heat of reaction of water in the gas state, I will just have to add this reaction, and then we can calculate the heat of reaction of this particular reaction where H2O is in the gas state. And that's called as calorific value. Calorific value per kilogram per meter cube. Higher calorific value when water is in the liquid state, lower calorific value when water is in the gas state. Okay? Or gross calorific value and net calorific value. Okay, just to emphasize different things, let's talk about different fuels. Let's talk about methane. Let's talk about petrol. So petrol we'll just say is C8H18. Diesel will not take, we'll take some other thing. Let me give you. Okay, let's just take these two only. So let me say standard heats of combustion in terms of kilojoules per gram mole. Okay, methane you already have. Methane you already have. What was the value that we taken? 890, right? 890.4. Kilojoules per gram mole. This is standard heat of combustion. Standard heat. That's why that 0 there. Combustion. That's why the C there. Now C8H18. Delta H is minus 5470.12. Okay. Cost. Methane is like, say, natural gas, or let's say natural gas, piped natural gas. Let's say cost is like rupees 30 per kg.
So CNG 50 per kg.
Okay, chalo 50 ले. Right, you're right. Right. Recently prices have gone up. Okay, 50 per kg. I was thinking more in terms of domestic, but okay, pipe natural gas is little cheaper than CNG. Okay, that's fine. 50 we can take. I mean, the values don't matter. What we are going to solve matters. Petrol, let's say 100 rupees per liter. And let me, let's say density is
0.760.
0.76 grams per centimeter cube or 760 kgs per meter cube. Same. Let's say I want to run my car based on either petrol or based on CNG. And let's say the car gives the same amount of mileage in the sense of amount per kg, amount of kilometers traveled per kg. So what we will actually talk in terms of per unit heat generated by combustion in the car. Methane is going to be combusted in the engine, or petrol is going to be burnt in the engine. So per unit heat generated by combustion, one, what is the cost of these fuels, and two, what is the CO2 footprint of these fuels. Okay, understood the question? And remember, in the engine, methane is going to be get burnt, and water I am going to get in the vapor state, not liquid state, because the temperature will be high. Pressure will be 1 atmosphere, but temperature will be high, maybe few hundreds of degrees centigrade. So water will not come in the liquid state. So that's the difference between the standard heat of combustion. Remember what we talked about. Standard heat of combustion, water in the liquid state, whereas actually when you burn something, you get water in the gas state. So to that extent, less amount of energy is available. Okay, shall we find this? Can you solve? Very relevant problem. You can advise somebody from your family whether they should go with CNG car or whether they should go with a petrol car or a diesel car or an electric vehicle now or a hydrogen car. Well, they are not available in India. Hydrogen is not available in India, but electric certainly are available in some pockets. Obviously, there will be more constraints in terms of cost and in terms of how I can refill, how easy it is to refill or recharge if it's an electric vehicle. What is the cost of recharging? convenience, ease of operation, ease of maintenance. So many other constraints happen, but let's worry about two aspects only right now: cost and CO2 footprint. Okay, can you solve? I hope you have seen all that calorific value videos. How many of you have seen that calorific value video?
Seen it, sir.
Yes, sir, I have seen.
Okay, two people.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
How many of you have solved the evaporator problem? How many of you have seen the evaporator solution using Excel, using manual calculations?
Sir, seen it, sir.
Yes, seen
Yes, sir.
matlab seen matlab done yourself and then solved, then seen.
Yes, sir. Yes, sir.
Even that Excel sheet, you can make that Excel sheet yourself. Not just watch the video. It's not like a YouTube video that we watch and we forget. You have to actually do it yourself. Okay, solve this problem. Anybody wants to have a break also for 5 minutes, they can have a break. But be in the same frame of mind. Don't start playing computer games. Just take a break if you want a glass of water, that's all. Otherwise, there is no break.
Sir,
Yeah.
sir, for CNG, I'm getting 2.78 rupees per kg. Oh, sorry, per kilojoule.
Okay. So you are taking basis as 1 kilojoule of energy that you want. Okay. Let me write some answers. Okay. And what you are saying. So 1 kilojoule as energy liberated. That's what we want. Okay. So what is the cost coming to for CNG?
Sir, for CNG, it is 2.782, and for octane, it's
Rupees
6.31. Yes,
2.7.
2.782,
Okay. And for octane it is
6.31.
6.31. And what is the CO2 footprint?
Sir, CO2 footprint for CNG is 2.75 into 10 power minus 3 tons of CO2 per metric ton of methane.
Nere Baba, per energy you have generated. Per energy generated, how much CO2 is liberated?
Okay, sir, I thought I have to give it in tons of per metric ton.
No, why? What are we doing? We are talking about per unit heat generated by combustion.
Sir, I saw footprint and we generated
No,
footprint
but
as.
CO2 footprint is per unit energy generated, na? So CO2 footprint would be in terms of kgs of CO2 per kilojoule of energy of generated by combustion.
Okay, sir, I will
Yeah,
do the
footprint can be in terms
needy
of
calculation.
any basis, no. So here, what is the requirement here? Here we want to generate energy, na. So
Yes, sir, I
we are
will.
talking in terms of CO2 that is generated to get to 1 unit of energy. And right now you are taking 1 unit as 1 kilojoule. Okay, fine. You just have to multiply by a factor, right? Any other answer for 2.78, 6.31? Any other answer? I think something wrong with it last week. Yeah, Praveen, done? Praveen, done?
Yes, for methane, it's coming 49.43 kgs per kilojoule.
49.43 kgs.
Yes, sir, per
Okay,
kilojoule.
or grams.
Sir, wait, I'll check.
So ठीक है, I'm writing 49.43 kgs, and for
And
octane,
octane, it's 64.35.
check your units.
Yes, sir, they're grams.
Don't worry, it happens. Any other answer? Any other answer? Mayur, any other answer? What takes so long?
Sir, I'm solving.
So long? We already have the answer for methane. We did it last time. In the same way, you just have to do for octane, that's all. Only 15 minutes. Only one answer so far. Any other answer? Anybody else? Nishant,
Yes, sir. I'm solving that.
Rishikesh,
Solving, sir.
कितना टाइम क्या लगता है? Ansh, any answer?
Sir, I'm getting the cost quite low. Like for the CNG, I'm getting 0.00089.
Rupees.
Sir, even
So
I'm
for me,
getting
it is
cost
even I'm
very low.
getting. Yes, sir.
0.00
0.089.
rupees.
So 9 and 10 power
Yeah,
4
rupees,
around.
rupees.
Yes.
Okay. 9 into 10 is to the power minus. That's fine because our unit is so small. 1 kilojoule is very small amount of energy. Okay,
And the other cost I'm getting is 0.0274.
so 100 times more, or maybe not 100, maybe 30 times more. Yeah, because our unit is very small, 1 kilojoule, a small amount of energy. That's fine. I mean, we just want to compare. So it is. And CO2, Ansh? CO2, how much are you getting?
I'm doing that. I'm doing that.
Okay. Praveen, check your answers.
Yes, sir.
Maybe you are right. Maybe they are wrong. Ansh and Anirudh, maybe they are wrong. Maybe you are right. Maybe all three of you are wrong. I don't know. Rishabh, any answer? कितना टाइम क्यों लगता है? Why are you taking so long? Om, any answer?
Sir, for CO2, I am getting the same cost. I am doing for petrol.
For CO2, you are getting same cost. Now CO2 is to be found out.
9 into 10 raised to power minus 4.
That is for methane as a fuel.
Yes, sir. Sorry,
And-
methane.
And how much CO2?
Not, sir. Not calculated.
Okay, calculate.
So for the amount of CO2 in methane, I'm getting 0.0546 gram.
Okay,
Yes, sir. 0.054 grams, sir.
okay. So 546, let's just say 55. Okay, and octane?
Yes. I'm calculating, sir.
Okay.
Sir, for the CO2 produced in case of octane, I'm getting 0.069.
0606
9.
0.069.
Yes, sir. Yes, sir. I also got same values.
Okay, so we'll just round it off 0.07.
9. Yes.
Let's just round it off.
Yes, sir. For octane, it's coming 0.0752.
Grams, right?
Yes, sir.
Praveen, check your answers.
Sir, I'm getting all the second set of values.
Mayur has vouched for these answers. That means they must be right. Okay, should we quickly solve or should we not solve? It is fairly straightforward for everybody. Somebody say something. Should we solve? Do you need more time? Should we? No need to solve. It is so obvious. No.
2 minutes, sir.
Yeah. Okay. Are you any answers?
Solving, sir.
What takes so long? I thought this will get done in 30 seconds.
Sir, are there the second set of values? Are their units same as mine?
Second set of values?
Are their units same as mine?
Yeah, everybody has told me in terms of rupees and grams.
No, sir. 1 kilojoule as equivalent.
Yes, sir.
Yes, sir.
Yes.
1 kilo.
Yeah, so everybody is saying yes for 1 kilojoule. You can take any and you can convert it into 1 kilojoule. Okay, I think let us try to solve. Maybe what we will do is we will do calculations for octane. So C8H18 at 25 degrees centigrade, 1 atmosphere, that's liquid. So if I burn that, I will get 8 CO2 and 9 water. And then I will require 25 by 2 oxygen, standard state. So oxygen in the gas, CO2 in the gas, water in the liquid state, and the standard heat of combustion, delta H, that's what we are told. Delta H is 5470.12. 5470.12 kilojoules per gram mole of octane. Right? This is all the information that we are given. Delta H exothermic minus. Right? When we are actually going to burn it in the engine, I will get C8H18 plus 25 by 2 oxygen in the gas. It will give me 8 CO2 in the gas and 9 H2O in the gas state. That's what is actually going to happen in the engine. This delta H, this is what we want. Okay. How will I go from this to this? If you remember your calorific value video, I add the reaction. If you add these two reactions, you will get the third reaction. And for this particular reaction, delta H, we already know, we have got that last time. We have got that as 44.1 kilojoule per gram mole of water. 44.1 kilojoule per gram mole of water. Recall our last time's lecture. If you don't recall, look at the recording. This is 44.1 kilojoule per gram mole of water. So I need to multiply that by 9 because I have to add 9 gram moles of water on the left side, 9 gram moles of water in the vapor state on the right side. So for this particular reaction, what is actually going to happen in the engine, delta H would be minus 5470.12 plus 9 times 44.1. So if you calculate this, minus 5470.12 plus 9 multiplied by 44.1 kilojoules per gram mole of water into 9. So this will be minus 5073.22 kilojoule per gram mole. Okay. So if I am taking if we want to generate 1 kilojoule of energy by combustion in the engine, gram moles of C8H18 required. What would that be? 1 kilojoule is what is required, divided by 5073.22. That is the energy that I would generate by way of combustion. So 1 divided by 5073.22, these many gram moles. So this is 1.97 into 10 raised to minus 4 gram moles of octane. Molecular weight of octane. Molecular weight of octane would be molecular weight of octane.
240.
I'm not talking 140. Therefore, grams of octane required. (1.97) into 10 raised to minus 4 into 114. How much is this? Somebody calculate. You are present in the class, so you have to calculate and answer.
224, 158.
224.58. Alankar, is that you were answering?
Yes, sir.
This is what? Units or what? What are the units?
Into 20 to the power minus 4, sir.
Alankar, I am asking so many dash and grams. What is the answer?
Sir.
What is the answer?
Sir, 0.0225.
Right. 0.0225 grams. Okay. So if density, what is the density that we have given?
So 0.76.
0.76. 0.76. 0.76 grams per centimeter cube. So what would be the volume of C8H18? This would be 0.0225 divided by 0.76 grams per centimeter cube. Okay. And then if I want it in terms of liters, this will be in terms of centimeter cube. If I want it in terms of liters per centimeter cube. So if I take 1 liter, that's 1000 centimeter cube. Converting units, 0.0225 divided by 0.76, so many centimeter cube divided by 1000. This would be 2.96 into 10 raised to minus 245, 10 raised to minus 5 liters. So cost 2.96 into 10 raised to minus 5 liters. Cost, how much I took? 100 per liter. So into 100, 2.96 into 10 raised to minus 2 rupees. 2.0296 rupees. Right. This is right. Praveen, have you found out your mistake?
Yes, sir, I found out my mistake.
Okay. Now CO2 generated. CO2 generated. How much CO2 generated? How much gram moles of C8H18 are required? 1.97 into 10 raised to minus 4 gram moles are required. Every gram mole of C8H18 burns, we are going to generate 8 gram moles of CO2. So CO2 generated would be 8 multiplied by 1.97 into 10 raised to minus 4. 8 multiplied by 1.97 into 10 raised to minus 4. This will be in terms of gram moles. If I multiply by 44, this would be in terms of grams of CO2. So 8 multiplied by 1.97 into 10 raised to minus 4 multiplied by 44 molecular weight of CO2, 0.069 grams of CO2. Okay. Everybody comfortable? Yes, no?
Yes, sir.
Yes, sir.
Yes, sir.
Can we go to the next problem?
Sure, sir.
Now we have covered the basics. Now we are going to go to problems. Okay, so here is a problem. Remember when we had our SO2, sulfur and SO2, sulfuric acid manufacture. So we had a gas stream that was going to a reactor. After sulfur was burned, in the gas stream we had SO2, we had oxygen, we had nitrogen. So let's say SO2 is 9%, oxygen is 9% in terms of mole percent, and nitrogen 80, so 82%. Okay. So this stream, let's say it is coming in at 1 atmosphere absolute pressure. Temperature is 300 degrees centigrade. After burning of sulfur, this goes into a catalytic reactor, catalytic converter. Vanadium pentoxide is your catalyst. SO2 reacts with oxygen to give us SO3. All right. Do you agree? And then this SO3 gas, containing the gas, it will still have nitrogen, it will still have some unreacted oxygen, it may have SO2, it may have SO3. If SO2 is completely converted, if conversion is 100%, then there will be no SO2. But if conversion is less than 100%, say it is only 50% conversion, then we will have some amount of SO2 remaining, SO3 generated, unreacted oxygen, and nitrogen, of course, that is our inert. Okay. What I am going to give you is two things. I want this temperature to be 450 degrees centigrade. I don't want this temperature to be more than 450 degrees centigrade because the catalyst may get damaged at high temperature. So I want to limit the temperature. I want you to find out how much percent conversion of SO2 will take place in the reactor. And remember what we are saying, this reactor is adiabatic, meaning no energy is added, no energy is taken out, except now reaction is occurring. This reaction, I will tell you the data about this reaction, SO2 going to SO3 reaction. So I will give you standard heats of formation for SO2. I gave you that last time, but I think I will give it to you again so that you don't have to keep on looking back in your notes. Minus 296.9 kilojoules per gram mole. Standard heat of formation of SO3 is minus 395.18 kilojoules per gram mole. I will also give you the Cp values. Cp is A plus Bt plus Ct square. Cp is in terms of calories per gram mole Kelvin and temperature in Kelvin. All right. Cp in terms of calories per gram mole Kelvin, temperature is in Kelvin. I will give you the A, B, and C values. So A for different gases, B into 10 raised to 3, C into 10 raised to 6. I will give it to you for different gases, O2, N2, SO2, SO3. 6.117, 6.457, 6.945, 7.454, 3.167, 1.389, 10.01, 19.13. C values minus 1.005, minus 0.069, minus 3.794, minus 6.628. These are the values of specific heats, constants A, B, and C. Okay. So I want you to find out how much conversion of SO2 should take place in the reactor so that the outlet temperature reaches 450 degrees centigrade. Okay. Can you find this? If you think you need more data, you can always unmute yourself and ask. I'm listening. If you think you need additional data, ask. I will give you whatever data you want. Everybody understood what is to be found? Has everybody understood what
Yes,
is
sir.
to be found? Yeah.
Yes, sir.
Excuse me, sir.
Yeah.
Yes, sir. So basically, the reaction is happening at 300, and the heat released is used to increase the temperature to 450.
Yeah. Okay.
So
If that's
is
what
it
you
like
think,
that?
I don't know. If that's what you think it is. Yes, it is. At the most, I will say enthalpy is a state function.
Yes.
So answer, Ansh.
What, sir?
Answer.
No, I'm calculating.
Praveen, any answer?
Sir, calculating. Sir, reaction is happening at 300, right?
So no, we
Reaction
have a
is
calculator
happening.
that can do integrations for you.
Sir, reaction is happening at 300, right?
I don't know. Same answer that I gave Ansh. I only know that enthalpies are a state function. I do not know.
Sir, and heat of formations are given at 25 degrees Celsius, right?
Standard heats of formation. This zero indicates standard heats of formation. Standard heats. And F indicates formation. Haven't you seen in in your textbooks appendix that I showed last time? Delta H0F, delta H0C. Himmel Blau's book. You have that book, right? Appendix. Any answer?
44%.
Pardon? 40?
44%, sir.
Okay, Atharva. 44%. That's one answer. Let me just write that somewhere. Very nice, Atharva. Okay, so what we will do is we will stop here for the day. You have another class at 10:40, so we will stop here. You can have a break of 10 minutes as well. But try to solve this problem, right? So we will see the answer on Thursday, but try to solve and see what answer you get. I'm not saying whether this 44% is right or wrong. Okay, maybe it is right, maybe it is not right. I don't know. So you find out for yourself what is the answer. Discuss amongst yourselves. Okay, so we will go forward from here on Thursday. Shall we close for the day?
Okay, sir.
Sir.
Okay, sir.
Thank you, sir.
Yeah, if you have any doubts, you can just ask each other. You can